I'm going to talk through a simple implementation of Monte Carlo simulation, which is one way that we can use stochastic methods to explore a system. I've given some text here to explain what's happening. The idea of Monte Carlo, this is often known as Metropolis Monte Carlo, is you evaluate the energy of a system in some starting configuration. Often it's a random initial state. You make some small change to the system. Again, that change is random. You evaluate the change in energy, that gives you a change delta E. If the energy goes down, you accept the change with probability equals 1, that's the standard. And if the energy goes up, and this is the key thing, is you accept the change with a probability which is proportional to minus delta E. What this means is that there is a finite chance of the energy going up. Now, the key parameter in that probability, as you can see here from this formula, is that it's delta E over KT. So we introduce some kind of temperature, and this allows us to explore many different possibilities. So in particular, the approach of a system to equilibrium at some finite temperature. Obviously, setting the value of T either has to come from some experimental situation that you're trying to reproduce, or possibly by some judgment related to the energy scales in the system. So that basic algorithm is fairly simple. Implementation quite often involves a couple of different issues. First of all, there's the question of how you make the change. How do you decide how to do that? And secondly, how do you evaluate the change in the energy? So we're going to demonstrate this with a very simple model I made up of sedimentation. We've often used icing models, but this is maybe slightly simpler. And the idea here is simply that you've got a bunch of particles of different mass on a square lattice, which are settling under some kind of external gravitational force. We start with random masses at the different arrays, and we just look at what happens when you swap neighboring particles with the same x coordinate. So the potential energy, the gravitational potential energy, is simply the mass of the particle multiplied by its y coordinate. And so you can imagine that if you have a lower mass at y and a higher mass at y plus 1, or let's say j and j plus 1, then swapping those two would make the energy go down. And if you have the heavier mass at j and the lighter mass at j plus 1, if you have a high enough kt, there is a possibility that you can swap that. Now, this isn't anything that you're going to use to model sedimentation, but you can imagine the kind of experiment you used to do in school where you take a jar of dirt, not as Jack Sparrow does, and you add some water to it, and then you shake it up, and you see the soil or the dirt settling out into different layers. It's that kind of idea. So let's set this up. We're going to need to have a random number generator. So we'll do RNG is equal to numpy.random.default RNG. We'll set up a number of sites. Let's say n is equal to 20, so it's going to be a square array. We'll have a maximum mass, say max m, which is going to, let's say, equal 6. And we'll create an array of positions. So we'll say, actually, no, sorry, what we're going to do here is we're going to create an array of y positions to enable us to calculate the total energy of the system efficiently. So we're going to call that yvec, which is going to be numpy.arange of 1, n plus 1, because I wanted to go from 1 to 20. Actually, no, that doesn't matter. We don't care if it starts at 0, so let's leave it as n. Okay, we're going to have a lattice. And I'm going to say lattice 1 because we're going to do this a couple of times. And this is going to be rng.integers of 1, max m plus 1, and then we want the shape n, n. So we're creating an array here where the integers go between 1 and a maximum weight. Let's just check actually. rng.integers, why is that not showing me the, okay, low, high, exclusive. Yes, okay. So the reason I was just checking there is because I'm wanting to know whether this second argument is inclusive or exclusive, and it's exclusive, as a lot of Python arguments are. So in order to go from 1 to our maximum mass, which in this case is 6, we have to do max m plus 1. Let's just plot that to make sure we know what's going on. The plot of lattice, lattice 1. Okay, that makes sense. That looks about right. Now we need to put a color bar on there. PLT color bar. Okay, there's our color bar. And actually, I'm going to put the origin at the bottom left. Origin is equal to lower. Okay, that's our initial starting point. It all looks very nicely random. We've got the color bar neatly laid out. If necessary, you can add an argument to color bar to set the ticks, but we're not going to do that because that's worked. Now, just a note, when we're dealing with arrays in Python, the first index gives you the row. So when we do this sedimentation, we're going to end up with all of the yellows at the left-hand side and all of the dark blues at the right-hand side, not vertically as we might expect from a simple gravity. So let's do a first trial. Let's set up n trials is equal to, let's say, 100,000. Let's do KT1. It's going to equal 5. That's taken on the basis that we've got a mass that's going from 1 to 6. And when we swap two masses around, the change is going to be of the order of, let's say, somewhere between 1 and 5, because we've swapped them by 1 unit of height and we've got a maximum change in mass of 5. So I'm putting KT as that kind of area because that's going to introduce quite a lot of randomness. And we're putting energy 1 is equal to numpy.zeros of trials, n trials. And then for t in range n trials, oops, put the column outside. What do? We will do the following. We'll say that pos x is equal to rng.integers of 0, n. Pos y is equal to rng.integers of 0, n minus 1. And that's because we don't want to include this final set of y values because we're always going to be comparing with y plus 1. And there are ways, of course, of generating a pair of integers here. I'm just doing this because it's simple. And then DE is going to equal, we've got lattice 1 of pos x comma pos y plus 1 times pos y. So that's what happens when we take the initial, that's the energy of the initial particle moved up, plus lattice 1 of pos x comma pos y, that's the mass at xy, times pos y plus 1. So that's the total energy after we've swapped. So yes, I think I said something wrong there. The first point here is the mass, the higher mass multiplied by the new lower position. This is the lower mass multiplied by the new higher position. And we now have to subtract off, and I'm going to put this in brackets, partly because obviously we want to put it in brackets, but also because it means I can split the line. And then we're going to say lattice 1 of pos x comma pos y times pos y plus lattice 1 of pos x comma pos y plus 1 times pos y plus 1. Good. Okay, so that's the starting energy, and of course I could have written two variables and subtracted them. There's always different ways of doing it. We'll say that the probability P is equal to numpy.exp of DE divided by KT1. And now we come to the crunch point. If DE is less than 0.0, in other words, if the energy's gone down, or rng.random, a number drawn between 0 and 1 from a uniform distribution, is less than P. In other words, so if P is, I forgot to put a minus sign in my exponential, that would have been disastrous. So if the change in energy is very large, in other words, if we get a very large increase in energy relative to KT, the probability will be small, and therefore the chance of this happening is small. So that makes sense. Now we want to do a swap. The simplest way to do a swap is as follows. TMP is equal to lattice 1 of pos x comma pos y plus 1. So that's the new. So now we say lattice 1 of pos x comma pos y plus 1 is equal to lattice 1 of pos x comma pos y, and then lattice 1 of pos x comma pos y is equal to temp. Okay, so we start off by storing the mass, the higher mass, we change the higher mass to the lower mass, and then we restore the lower mass. And then we say energy of T is equal to numpy.sum of lattice 1 times y vec. And the way that Python works, it will do an element by element multiplication, and it'll essentially scale every mass at each y level by the y coordinate, because that's how we set up yvec up here. Right, let's see if that worked. No, it didn't work because I used energy instead of energy 1. Okay, let's try it again. That did work. Let's now try and plot it. So plt.imshow of lattice 1, and we'll do origin is equal to lower. We'll do a color bar, and we'll do a title. We'll call it, make it a formatted string, so final distribution for kt is equal to open curly, close curly, kt1. Okay, that's given us the right title. We can see that there is a general sedimentation. So if you compare, this is the starting point where it's all fairly random. Here, there's definitely more yellow on the left than on the right. But let's just check that. So we've got this this large scale parameter that's monitoring the state of the whole system, the energy. So let's plot that. Plt.plot of energy1. What do we see? Okay, we see something quite reasonable. We start at a high energy, it comes down, and then it settles at a certain level where there's quite a lot of noise. Now, this noise is all thermal motion. So that's indicating to us that our KT value is quite large, which we knew. We set it like that. Okay, let's do it again. So I'm gonna copy everything just because that makes life quicker and easier. The only thing I'm going to change is I'm going to change the number of the value of kt. So I'm going to call this lattice 2. That's fine, good. Let's copy this. I'm not going to change end trial, so I won't copy that line. But I'm going to have to change kt to be kt2. I'm going to make quite a drastic change. I'm going to divide that by 50. There's my energy 2. So now I have to change all of my lattice 1s to lattice 2s. I'm sure there are more efficient ways of doing this. KT2, lattice 2, lattice 2, lattice 2, and lattice 2. And again, we change these. There we go. So let's run that. Good, that seems to have run perfectly happily. I'm now just going to steal an idea, which is to do subplots. Turns out you can do subplots using the simple PLT interface, though there's less control. I mean, this is always true with the PLT interface. Rather than creating a figure, there is always less control. So let me actually plot both of these, because I think it'll be good to have the contrast. So that's there. I'm going to copy all of that. There we go. So I'm going to say the second plot, I'll have lattice 2, and I'm going to have kt2. There we go. Oh, that's horrible. Crikey, let's change those color bars. There's a parameter you can put in color bar, which is shrink. And let's make that half the size. Let's see whether that's enough. There we go, that's a much more reasonable color bar. Okay, now let's just stop and take a quick look at this. So the left-hand side is the one that we did first. The right-hand side is the one I've just done here. And you can see we've got KT in the title. And so with a smaller KT, we see that we've got a much better looking result. This does still look somewhat jiggly and messy, but remember that we're not making any lateral changes, we're not changing X. So this is just sorting along the Y-axis. The final thing that we can do is we can plot a graph of the energies, and I'm just going to copy and paste some code I've got for that there. Energy, no, it's energy 1, not energy, there we go. KT should be KT1. You can see that I did this before and I'm just kind of reusing it. Okay, so now here's the plot of our energy over against time for the two different values of KT. You can see that in the first instance, where KT is 5, we stop at quite an elevated energy in the second instance, we got dropped down to what must be the absolute minimum for that arrangement of columns. So this illustrates quite a lot of different things. I mean, you can see here the effect of entropy. This is giving you some kind of sense of free energy that we could introduce to the system. You can also see the effect of KT. This has been a very efficient, relatively efficient way of getting to the ground state. I mean, you can see that actually with a low KT, we were done within a few thousand moves. For a 400 site array, that's probably not the most efficient way of doing it, but it's a very cheap and easy way to explore it. So the key ideas here are creating the total energy or the energy change, which we've done here with this DE, and then using this kind of Metropolis Monte Carlo idea of a test. I'll post the notebook on Moodle and also in my in the GitHub repository, which I'll link to at the bottom of the YouTube video. But that's how we do Metropolis Monte Carlo and use stochastic methods.